Today we're going to look at three-dimensional coordinate systems. I think you're going to find this topic really interesting because we live in a 3D world after all, don't we? And potentially up until today, we've been plotting everything in, two dimensions. And so we're going to kind of see how this relates to the real world. And as you continue through your mathematics or engineering or physics, whatever else you might be taking, you're going to see three-dimensional coordinate systems come up a lot to kind of as a way of plotting our world. So let's actually start out with the very beginning, I guess you could say, thinking about one dimension. And so if we were to graph a single number, we would just need one line, and that is the real number line. We haven't really worked with, we work with number lines sometimes, but we've kind of gotten to the point where we generally look at the two-dimensional coordinate system the most often. But kind of, again, going back to basics, the single number line here, we begin with a point, the origin, right here. And then we have just one single axis, which is very commonly going to be just the x-axis. And we can plot various numbers on here, right? This would be our positive x-coordinates, this would be our negative x-coordinates, etc. And we can graph things on a number line in various ways. Taking that to the next level, the next dimension, so to say, we can take two real number lines that intersect perpendicularly. Remember, that means they meet at a 90-degree angle at the origin. So the origin being where the two perpendicular lines intersect one another. Most often we have an x-coordinate and a y-coordinate. X-coordinate is generally our input axis, our horizontal axis, and the y-coordinate is generally our vertical axis, our output axis. If we were to want to graph in 3 dimensions now, what we would need are 3 number lines that all intersect perpendicularly. So the idea is that what we can do is we can take, I'll show you a few different ways you can think about this. One way would be if you think about taking this 2-dimensional coordinate system, you can add a 3rd dimension by thinking about an axis coming out of your screen towards you, towards your face. So another way that you could draw that, because I can't really draw out of the screen, is you can also draw it kind of sideways like this and kind of imagine that it is coming out of the screen. And so what you have here is this right angle, and this is a right angle. And what else am I missing? That doesn't look right. There we go. A right angle. So let's see, I've got this one, and then you'd have another right angle. Of course, it's this one, right where we had the original right angle. So that's another way we could draw this, and this then would be, we would need a 3rd number line, right? This you could call the z-axis. Okay, so this is one way to orient it. One way to orient the 3D coordinate system. But I'll show you, we actually generally will not orient it this way, and I'll show you why. We want this to follow what we call the right-hand rule, and I will explain the right-hand rule in just a second. Before I do that, let me show you the standard orientation that we will draw the 3-dimensional coordinate system. Okay, so that's going to be, generally we'll start out with kind of our usual, two real number lines that intersect, but this is not going to be the x-axis, and this is not going to be the y-axis. I'm going to actually leave them unlabeled for just a second. And then we take a 3rd line and we make that perpendicular here. So again, all of these lines in 3 space are perpendicular to one another. I currently only have the positive part of the lines drawn. If you wanted to draw the negative parts, you could make it, it doesn't have to be dotted, but I just like to do that to indicate that this keeps going in both directions, and the dashed ones represent the negative numbers on those particular axes. So let's actually label the axes. The standard orientation that we do is this is our x-axis, this is our y-axis, and the vertical is our z-axis. And then right here would be the origin, where all 3 number lines meet. Okay, so again, this is kind of our standard orientation. I actually recommend that maybe you go ahead and pause the video and just practice drawing a few of these if you haven't had much exposure with 3-dimensional coordinate systems. So I'll go ahead and draw it again from scratch. So again, you just basically start out with 2 perpendicular lines, and then you draw a 3rd one kind of coming out, and this is your x-axis, your y-axis, and your z-axis. So feel free to pause and keep drawing those if you need to get a little practice in there. But moving forward, so I mentioned the right-hand rule. So let's kind of go through what the right-hand rule is, because it will come into play when we start doing things with vectors. And so it's not going to be a huge thing right now. It's more just going to be something that we use to set up a standard for our coordinate system. That is, you know, the idea is that you can draw this three-dimensional coordinate system in any orientation that you want to, but if we have kind of a set rule or a set standard, then we can all be having kind of the same perspective on it, if that makes sense. So I'll describe the right-hand rule, and I'm going to show you a picture of it as well. So the right-hand rule is essentially what you do is you put your thumb should be thumbs up, like, hey, thumbs up towards the z-axis. Your pointer finger should be pointing in the direction of the positive x-axis, and your middle finger should be pointing in the direction of the positive y-axis. So basically what you end up having is your pointer finger, your middle finger, and your thumb all represent three different axes. And then you just kind of curl your other two fingers kind of in towards your palm. So your pinky finger and your ring finger. And hopefully you're doing this while I'm describing it. If you're not right now, go ahead and do that. So again, curl in your pinky finger and your ring finger. And if your friends walk in and go, what are you doing? That's okay. Just explain to them that you're doing calculus. And so then now you have your pointer finger, or sorry, you have your middle finger. That should be pointing kind of in a kind of awkward direction, kind of in towards your palm, but at a 90-degree angle. Your pointer finger should be pointing directly straight out in front of you, and then you're giving a thumbs up, and your thumb is pointing upward vertically. Now, if you didn't quite follow that, let me show you a picture, because a picture is worth 1,000 words. So the idea with the orientation of the axes is, again, your pointer finger is pointing in the direction of the positive x-axis. Your middle finger is pointing in the direction of the positive y-axis. Your pinky and ring finger are just kind of tucked away. We don't really need those. And then you have your thumb pointing up in the positive z direction. Another way you can do this, instead of using three different fingers, is you can kind of use your entire hand. I like this model for when I'm setting up just a 3D coordinate system and I just need to know the x and y and z axis. But I like this representation when I'm doing things with vectors. So I will describe these a little bit more once we get into doing things with vectors, more specifically the cross product. But the idea with this orientation is you would have all four fingers originally pointing in the direction of the x-axis. You should be able to curl your fingers towards the direction of the y-axis. So notice we can naturally curl our fingers towards the y-axis, towards our palm, whereas if I had my fingers pointing this way, it would be very difficult for me to curl my fingers that way, right? Our hand doesn't bend that way, basically. And so we'd have our fingers, all four fingers here pointing this direction, and then we would curl our fingers naturally towards the y-axis. And then naturally we would be giving a thumbs up towards the positive z-axis. Okay, so we're going to step away from the right-hand rule for just a little while. Again, we just really are using it to set up our three-dimensional coordinate system, but we will be using it again. So don't let it go completely out of your mind. It will come back in a little while. Okay, let's actually do a quick technology exploration using GeoGebra. So I'm going to pull GeoGebra up, because GeoGebra, now you probably noticed that sometimes we use Desmos and sometimes we use GeoGebra. And GeoGebra has a three-dimensional coordinate plotting system. GeoGebra is a very powerful software. And so we're going to be pretty much using GeoGebra from this point forward here in the class. So notice when we go here, we've got classic computer algebra system, 3D graphing. 3D graphing is what we want. If you were already using GeoGebra to do something else, like I tend to go and use GeoGebra Classic. So if you were kind of in here and you're already doing something and you don't want to go back to this GeoGebra home page, then you can either click on it from here, but once you start playing around, that thing disappears. So you go to the menu, go to perspectives, and then you can do 3D graphics from here. Okay, so now I have two of them open. I'll go ahead and close that one out. Okay, so here's the three-dimensional coordinate system in GeoGebra. Now, one thing that bothers me a little bit about GeoGebra is that they don't initially label the axes in here, but what you can do is just right-click and go to 3D graphics, and it will show you the standard for, you've got your tabs, x-axis, y-axis, and z-axis. This is where you can change your window if you want to. In this case, I want to label the axis. So I want this to be X. You can do drop down or you can just use your keyboard. X-axis, Y-axis, Z-axis. Okay, and then we'll go ahead and close that. And so notice that now they're labeled. I've got the X-axis, the Y-axis, and the Z-axis. And so notice that GeoGebra's 3D coordinate system does follow the right-hand rule in its kind of initial orientation. If you were to take your right hand, point your fingers in the direction of the x-axis, your fingers would curl in the direction of the y-axis, and your thumb would point up in the direction of the z-axis. Okay, or you can have your pointer finger in the direction of the x-axis, your middle finger is in the direction of the y-axis, and then your thumb naturally is in the direction of the z-axis. But the great thing about this is you can take this and you can move it around. And so notice that about, like right about here, is kind of where our drawn three-dimensional coordinate system is, right? The ones that we were drawing earlier. So I tend to kind of rotate it and look at it from here. Okay, and then we'll do a little bit of playing around with this, but one thing that you can do if you want to adjust your window is you can go to Move Graphics View, and then if you hover over a single axis, you can kind of zoom in, right, this out actually, zoom out or in a single direction, which is pretty handy. We will go ahead and play with that a little bit more, but let's keep moving forward and look at an example. So by hand, let's draw a set of rectangular coordinate systems in R3. So this notation here, I should actually probably come back up because I didn't quite describe that, did I? So what we have is we have any point in R3, and this is just saying the three-dimensional coordinate system because it's three real number lines that all intersect, right? And so the two-dimensional coordinate system, or 2-space, is labeled as R2. Okay, so this symbol here, you've seen this kind of in some previous videos. This symbol just means the real numbers. Okay. Okay, so moving forward here, let's go ahead and get some practice with plotting points in the three-dimensional coordinate system. So first thing I'm going to look at is kind of the size of our numbers to give me an idea of what my scaling needs to be. It looks like 5 is the largest, and then, so yeah, I think probably maybe a scaling from all axes going from -5 to 5 would be reasonable. So let's go ahead and draw our coordinate system first, and do your best to draw straight lines. If you have a ruler, now might be a good time to go ahead and take it out. They do have three-dimensional coordinate systems, like grid paper kind of idea, but we can go ahead and just do this by hand, just good practice. Here's our x-axis, again, our y-axis, and our z-axis based on the right-hand rule. Okay, and then I'm going to kind of keep this extended going back here, this way, and this way. Okay, and we can add length as needed to plot our points. So let's go ahead and start off with the point 1, 2, 3, right? Why not? So this means that we're going to go that x is 1, y is 2, and z is 3. Okay, so we're going to go ahead and go 1 unit, and let's go ahead and put our scaling in. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That looks good. Okay, so we're going to go 1 unit in the x direction to get us to here. Okay, we're not done yet though, right? We've gone 1 unit to get to the x direction. Now we need to go 2 units in the positive y direction to get to here. I'm still not done, right? I've done the x and the y coordinate. Now we're going to do the z coordinate. The z coordinate is up. I'm going to go up 1, 2, 3 units right here. Now I know you might look at this and go, Austina, that kind of looks like you're like making it what z equals 2. But remember that we're essentially just taking this distance here from this xy plane. You can think of this as like the floor, and then that's actually a great way of thinking about it, is here's a floor, here's a wall, here's another wall, right? Kind of imagine your own space that you're in right now. You can kind of imagine that as a three-dimensional coordinate system. So we've gone 3 units up from the floor, essentially, putting us right here. And so if you were to follow this along to the z-axis, you can see that it does, in fact, meet up with z equals 3. Okay, so that's the point right here then. And I'm going to actually go ahead and leave my path to get there, but this here is the point P, and we'll go ahead and label it accordingly. Okay, now let's go ahead and label, or do Q. I'll go ahead and do a different color for that one. 2, -1, 5. Here we go. We're going to start off with, again, now x is 2. That's right here. -1, so I need to show right about there would be -1. Okay, so I need to go in the -1 direction. Be right about there. And then we want to go 5 units up. That's about 1. That's about 2. That's about 3. That's about 4. And that's about 5. Okay, so that is the point Q. There we go. And let's actually, why don't you go ahead and do the last one. Go ahead and pause the video and try to plot the point 4, 1, -2. And come on back when you're feeling ready. Okay, welcome back. Okay, so we've got 4, that would be here, that's the x direction, 1 unit in the positive y direction, and then -2 units in the z direction. So now, rather than going up, I'm going to go down. So we're going to go down, and I think I have just barely enough space. We're going to be getting into the exploration here. There we go. There's our point R. Okay, now let's actually go ahead and plot these in GeoGebra as well, just so we can also get kind of a visual of how all these points relate to one another in space, and being able to kind of play around with the orientation a little bit. Okay, so I think I'll go ahead and do a split screen here so I can not have to remember what the points were. Okay, so we have the point P equals 1, 2, 3. There it is. So notice that what happens is we go over. Oh, here, let me do. I think I'll just go ahead and plot. No, here I'll just do large screen here. So I'm gonna make this back over to the move tool, and now I can see. Again, we've gone 1 unit in the x direction, which you can tell if you kind of orient it like this. 1 unit in the x direction. We've gone 2 units in the y direction. That would be this right here. And then we've gone up 3 units in the z direction. Okay? That looks pretty cool. All right, so the other one, now we'll do Q equals 2, -1, 5. And we can play around with that a little bit. So notice now it's, if this is the room that you're in right now, if you think of it that way, this is the floor, right? Wall, wall. The point Q is in the room next to you. It's in the room next door, right? And it's up fairly high. But probably not, if this is in maybe feet, it's not high enough to, you know, to go up through the ceiling or anything like that. Well, in this case, there is no ceiling. It just kind of keeps going up. Okay, let's take a look at the last one, which is the one that you did. 4, 1, -2. Now this point, notice, is below you. So that could be, depending on where you're at, if you're in a library or an apartment or something like that, then it's the floor below you. If you're kind of on ground, then the point R could be underground potentially. Okay, so there we go. There's our 3 points. And now let's start exploring things that go beyond just points, right? Points are interesting, and and everything, but let's take it to, you know, some equations. So let's imagine that we had x equals 2, pretty straightforward, and let's think about what that represents in R, that is the one-dimensional R, in R2, 2 space, and R3, 3 space. So let's start with 1 space. So in 1 space, this is simply a point. And we can actually go and we can plot it if we want to. Let's go back up to the beginning. And I'll use a different color, maybe orange. So, well, actually, let me do my scaling first. So if this is 1 and this is 2, then this would be x equals 2 in 1 space. If we were to look at x equals 2 in R2, now I think what I'll actually do is go ahead and erase this because we are, you know, I kind of use that to get us down here. So I'll keep this as the two-dimensional coordinate space. So x equals 2 in R2 would be, well, here it is in R1, right, just along the x number line. But now it's the idea is that x is 2, but y could be anything. And so what you end up getting is just this vertical line. Well, I'm attempting to make a straight line. This is x equals 2 in 2 space. Now in 3 space, x equals 2, maybe I'll do it here. In 3 space, we have x equals 2. Again, y can be anything. And so this is kind of the line, x equals 2 in 3 space. But now, just like y can be anything, z can also be anything. And so what we have happen is we end up having, well, z can be anything. So z can be anything, whether it be positive z or negative z. And we have this plane. I like to think of it as like a force field, right? If you're, like the laser beam has been turned on. I'm shading it in right now. That's what I'm going through this process here for. I don't remember how I have this set up usually. Larger. So you have this plane. So in R, again, 1 space, x equals 2 is a point, a single point. In R2, in 2 space, x equals 2 is a line, in this case a vertical line. In 3 space, x equals 2 is a plane. Okay, so imagine a line that then you've got this force field, laser beams going up and down in every, in every direction, creating this force field plane. Okay, pretty cool. Okay, so I'll summarize that here. Point, line, plane. And let's actually go ahead and visualize that in GeoGebra right now as opposed to doing all of these and then going to GeoGebra and doing all of them. So I'll go ahead and get rid of these. Delete. Okay, so x equals 2. Here we go. And notice what we have is, if I go like this, if I kind of go directly above the z-axis to a point where it almost disappears, this is now our usual xy plane, especially if I orient it like this, right? This is x equals 2 in two-dimensional coordinate system. And now I go, whoop, force fields up, right? We have this plane. So you almost think of it as like a wall. We just built a wall. Okay, cool stuff. Okay, let's take a look at some more. What does x squared plus y squared equals 1 represent in 2 space? And then what does it represent in 3 space? So in 2 space, I'll do this one over here. xy. In 2 space, hopefully x squared plus y squared equals 1 sounds familiar. It is the unit circle, right? Because it's using the Pythagorean theorem. It's saying the distance from the origin is always 1, is essentially what this is saying. And so the distance from the origin is always 1. I'm going to do my best to draw a circle. There we go. It's not too bad. and it comes out to 1 and 1, right? So this is, in R2, this is a circle. Now let's imagine that in R3. So if I were to take my three-dimensional coordinate system, again using the right-hand rule, and if I imagine the unit circle along the two-dimensional coordinate plane xy, what I would have is something that looks like this. I'll use a different color. Okay, so that's a two-dimensional circle that's lying flat on the xy plane. Now notice that this equation does not have a z in it, which means that z can be anything it wants to be, just like when you were growing up. And we have, again, kind of a force field kind of situation where everything's just going to go whoop and shoot upward, and what we'll end up having is a cylinder. I think I can draw better than that. Let me give that another try here. Okay, so we're going to end up having, and it can go downward as well. We'll end up having a cylinder. Let's go ahead and visualize that in GeoGebra as well. Go ahead and put my conclusion there first. Cylinder. Okay, let's see. Go ahead and get rid of that. X squared plus y squared equals 1. Okay, so notice again, if I take this and I kind of rotate like that, it almost actually disappears, doesn't it? It's hard to see, but it looks like it's our unit circle, right? And then as I kind of reorient it, I can see that it is a cylinder. Okay, pretty cool. All right, let's think about y equals x squared. What does that represent in R2? What does it represent in R3? So we know in R2, x squared is a parabola, like so. And so if we imagine it in R3, I guess I have a ton of space up here, don't I? Don't I? Look at all that space. I might as well use that. Okay, so extending that into R3. Okay, well, again, go ahead and graph y equals x squared. So y equals x squared would look like this along the xy plane. And then, again, z can be anything, so what we have is this kind of just extends upward, like so. And we have kind of this, I'm not sure how good, that's pretty terrible. Thank you, GeoGebra. Let's go ahead and see how it looks in GeoGebra. But the idea is that you have this, this parabola that then extends upward and downward vertically. So we'll take this and do y equals x squared. There we go. GeoGebra does a much better job at this than I do. And if we take this and kind of, again, hover over the z-axis, we can see that xy coordinate plane and see the two-dimensional projection on that and see that it's a parabola. And then if we kind of, keep that perspective of seeing the z-axis, we can see this kind of parabolic sheet, I guess you could call it. I think there actually is a word for this, and I'm totally blanking on what it is. I'm going to actually pause this and look it up. Give me one sec. So I actually don't think there is a name for this. So this gives us a good opportunity to name it whatever we want to name it. I'm kind of liking parabolic sheet. So let's go with that. All right, so in R2, this is a parabola. And in R3, I'm going to put quotes because we just kind of named this up, made this up, parabolic sheet, question mark? Sure, let's call it that. Okay, and then let's talk about z equals 1. What would that represent? Okay, so so notice this doesn't ask about what does this represent in R2 because we can't represent z equals 1 in R2. There is no z axis in R2. So in R3, what this would be is we would have, I think I'll go ahead and do this one over here. X, Y, Z. So it's basically saying z equals 1, right? Z is 1. But then x can be anything and y can be anything. So what we have is this. So x can be anything, y can be anything. And what we'll end up having is another plane. But now rather than it being like a vertical plane, like a wall, it is a horizontal plane. You can think of it as kind of like a ceiling. So this is, again, another plane. In this case, it's kind of like a plane that represents a ceiling. And just for good measure, why not plot this in GeoGebra as well? And notice I do z equals 1. And you can change the color on these, by the way, if you just, let me go ahead and go full screen here. If you just if you right click and go to settings, you can go to color and make it whatever color you would like. And it's kind of cool to see like when certain surfaces intersect one another. That's what these graphs are called in 3 dimensions. They are called surfaces, and we will get into those a little bit more. So yeah. It's kind of cool to plot multiple ones and kind of see how they interact with each other, and we'll have lots more time to explore that. Okay, well, let's talk about distance. We've been talking about points, and anytime we have multiple points, it's kind of nice to talk about the distance between them. And if you recall, in R2, the distance between 2 points was given by this distance formula, and the way that worked is that if you had some point, I'll just go ahead and draw like some point here and some point here, for example. So let's say this was like x1. Let me zoom in a little bit. If this was x1, y1, and this is x2, y2, then the way that we find the distance between them, that would be this length, is we kind of just create a right triangle, right? Because the axes meet at 90 degrees, so I can construct a right triangle here. And notice that this length would be the change in x's. It would be x2 minus x1. And this length would be the changes in y's, y2 minus y1. So you end up getting that this side squared plus this side squared equals this length, which we were calling d, this side squared. And you just square root both sides, and voila, you get your nice distance formula. Now we can take that same idea if we have 2 points in 3 space, then we can find the distance between the 2 points in a very similar manner to finding the distance in R2. We essentially can just take the distance would be the square root of, if we take the change in x coordinates squared plus the change in y coordinates squared, and then now we'll also take the change in z coordinates squared. Square root of all that will give me the distance between 2 points in 3 space. Now, this extension of the distance formula should feel relatively intuitive, but it's not exactly like a proof. It's just like oh, it feels like we should be able to do this. But let me show you kind of geometrically why we can do it this way. So here's a diagram, and we've got 2 points. This is the point, right, x1, y1, z1. And this right here is the point x2, y2, z2. And we're trying to find the distance between those 2 points. Right, so this distance here, d. Now we already know from the distance formula, so this, notice we have the right-hand rule orientation, x, y, z, as we should. And this length here then, this is just a line along the xy plane, and I can see that it would create a right triangle here, right? And so I have that this length is the change in x's, this length is the change in y's, and so this length here is using the distance formula, right? The square root of the change in x's squared plus the change in y's squared. So same idea as the two-dimensional distance formula that we had before. So that's this length here. Now I know that this length is just a vertical length. It's just a change in the z-axis. So this length is z2 minus z1. And notice that what we have is a nice right triangle. So we can again use the idea of the Pythagorean theorem. We have this side squared, which notice would square the square root. plus this side squared would equal this side squared, and there is our distance formula. I'll go ahead and write that out. The distance squared would be the square root of x squared minus x2 minus x1 squared plus y2 minus y1 squared, but squared, right? Plus this side squared, z2 minus z1 squared. And so notice we get that distance formula that we intuitively arrived at here. Okay, so moving forward, here's the distance formula here again as well. And so a few different ways that you can represent distance. I used a d in the previous one, but you can also use these kind of two vertical lines to represent the distance between the 2 points P1 and P2. And you'll also notice us use that notation later when we look at magnitude of vectors, because magnitude of a vector is really the length of the vector, which is the distance between the starting point and the ending point. So that notation will kind of come into play even more later. Let's do an example. Let's find the distance between 2 points, 1, 2, 3, and 2, negative 1, 5. I believe, yep, those were 2 points that we looked at and plotted earlier. Here they are. And now we're going to find the distance between them. Here we go. I'm going to show you also how to do this in GeoGebra because it's cool to visualize it and then also to just kind of know how to do it in multiple ways. So let's find the distance between these 2 points. We'll use the distance formula. So the distance between P and Q is going to be the square root of, now we will subtract, now you probably remember this from using the distance formula in R2. When we subtract, we just need to make sure we do it the same direction. That is, it doesn't matter which one we pick to be x1 or x2, we just need to make sure that we're consistent. So if I want this to be x1, y1, and z1, then this would be x2, y2, and z2. And I just need to make sure that my subtractions go 2 minus 1, negative 1 minus 2, 5 minus 3. So just make sure you go in the same order. I'll go ahead and write it out. 2 minus 1 squared plus negative 1 minus 2 squared plus 5 minus 3 squared. That gives me 1 squared, which is 1, plus 3 squared, which is 9, plus 2 squared, which is 4. And I end up getting the square root of 14. There are no nice perfect square factors to 14, so I'm just going to keep this as the square root of 14. This is the exact distance. If we wanted to, we could get a decimal approximation for that. It should be somewhere between 3 and 4, closer to 4 since 14 is closer to 16. And let's go ahead and see. There's that image I stole. Okay, all right, let's just go ahead and put in square root of 14 for right now, just so I can get a decimal approximation for that. It's about 3.74. As we expected, it was between 3 and 4, but closer to 4. And let's go ahead and check our answer in GeoGebra by getting rid of all of this stuff. I'll go ahead and leave that there. Okay, so again, it was the point P equals 1, 2, 3, and Q equals, oh, let's see if I can remember it, 2, negative 1, 5? Is that what it was? I'll double check. 2, negative 1, 5, yes. Okay, so now we have these 2 points here, P and Q, and we're, again, going to try to find the distance between them. And so what we can do is go up here to the segment tool, and we're going to create a segment between 2 points, between the point Q and between the point P. It doesn't matter which order you do that dragging in. You could have clicked P and then Q, either way. And notice it shows that the length of the segment is 3.74. If you want a little more precision than that, then what you can do is go to the menu and go to settings, and you can extend the rounding a little bit more. Maybe you want 5 decimal places, wherever you are thinking you want to go with rounding. So about 3.74 is the length. Notice it just gave a decimal approximation and not an exact value for the length. The distance formula will give us the nice exact value. All right, now why don't you go ahead and give this a try. Find the distance between the 2 points Q and R, and then come on back when you're done, but also go ahead and check your answer in GeoGebra before you come back also. And that way you get some practice with GeoGebra as well. So I'll see you in a second. Well, hopefully more than a second. I'll see you in a few minutes. All right, welcome back. Let's go ahead and go over this one together. I'll do this relatively quickly since you already have kind of gone through that process. Now, a lot of this subtraction you can probably do in your head and maybe even doing the squaring as well. 4 minus 2 is 2. 2 squared is 4. 1 minus negative 1. Now, careful with these negative signs. 1 minus negative 1 would be 2. 2 squared is 4. Negative 2 minus 5 would be a negative 7. Squared is 49. Okay, lots of room for little sign errors there. So, okay, so then we'd have, let's see, 8 plus 49 would be 57. And similar to 14, 57 does not have any perfect square factors. I believe 57 is actually, nope, 57 is not prime though. 3 goes into 57. Let me double check. Well, it'd be 3 times 20 is 60, so 3 times 19 would be 57. So no, it does not have any, it doesn't have any perfect square factors. And we get about square root 57. It's about 7 point, I feel comfortable rounding that to 7.55. Now let's double check our answer in GeoGebra. R equals, now I've forgotten this point, 4, 1, negative 2. There we go. And notice that the distance between point the distance between point Q and R was larger than the distance between point P and Q, which looks visually correct. So I'm going to again go over here and select segment, select the point Q, and then select the point R. And it gives me that the length of the segment is about 7.55. So same as what we got before. It's kind of cool. It does dotted when it's kind of like you're looking, when it's like the floor XY plane is taking shadow over it. And then you can kind of see, yeah. Okay. All right, now let's do another exploration here. Taking that distance formula and kind of extending it forward, we're going to start talking about spheres. So let's let the point XYZ be a point on a sphere. It looks like we've got on a sphere of a sphere, on a sphere of, there we go, a sphere of radius r and center at the point HKL. Find an equation for the sphere. Well, the great thing is that we know that circles and spheres, right, a circle is just 2 dimensions and a sphere is 3 dimensions, have kind of this similar geometrical property in that they are, every point on that circle or sphere is equidistant from the center. In that case, the equidistant length is the radius r, and the center being HKL. So we can use the distance formula to describe this. That distance is r. So I can say r squared is going to always be, and actually maybe I'll just use r instead of r squared. We'll just do r equals the square root of, so we would have the distance between the 2 points, the center and the point P. So x minus h squared plus y minus k squared plus z minus l squared. Now actually most of the time we don't represent this with a square root, because if I did, I would need to do both the positive and the negative. When we talk about distance between 2 points, that's always going to be a positive number. But in this case, so I'm just going to do r squared equals x minus h squared plus y minus k squared plus z minus l squared, which notice gets us our point right here. So this is something that you want to remember, but it's really just an extension of the distance formula, so it's not too hard to remember it. Let's use it to find an equation of the unit sphere centered at the origin. So we already know the unit circle is x squared plus y squared equals 1, right, in 2 space. And so now we're going to look at the equation of the unit sphere in 3 space using the equation of a sphere in 3 space. So in this case, we would have, since it's centered at the origin, then that means that the center is the point 0, 0, 0, right? And so that means h, k, and l are all going to be 0. And then since it's the unit sphere, that means that the radius is going to be 1. So using this formula, we would have x minus 0 squared, which is of course just x squared, plus y minus 0 squared, you get the idea, plus z squared equals the radius squared. 1 squared is just 1. So this is the unit sphere centered at the origin. Let's double check in GeoGebra. So what you can do is you can use these buttons if you don't want to delete things and you think maybe you might use it later, you can just hide them. So x squared plus y squared. And notice you see some cool things as you go because it graphs as you go. So feel free to play around with it a little bit. Equals 1, and there we go, we've got our nice unit sphere. It almost doesn't look completely spherical just because of the axes. If you wanted to make it look more spherical, you could kind of bring it in a little bit. Now it looks a little bit better, a little bit more like a sphere. Okay. Let's go ahead and look at another sphere, but we're going to have it centered somewhere else. And notice we are not given the radius in this case. It just says the center is this point and the sphere contains this point. So we know the center is 1, 2, 3, and that's a point that we've been working with so far. And here's the point Q to negative 1, 5. So we know that the center is going to be representative over here with the H, K, and L, right? This is going to be H, K, and L. It's the center. And then we know that it contains this point, right? And so the question being then, what is the radius if it contains this point to negative 1, 5? Well, that's really the distance, isn't it? It would be the distance between those 2 points. And so we actually have found that already. The radius is going to be the distance between the point P and Q. And we found that to be the square root of 14, right? Let me just double check. Yep, distance was square root of 14. Now we're going to leave that in the exact form of root 14, not its decimal approximation of 3 point whatever. Okay, so that's the radius, and again we know the center is the point 1, 2, 3. So that gives us then the equation of x minus 1 squared plus y minus 2 squared plus y minus, z minus 3 squared equals the square root of 14 squared, which would be 14. Okay, so there we go. That's the equation of the sphere that goes through these 2 points and has the center at P. Let's double check our answer because it's nice. See, I'm really glad that I didn't get rid of point P and Q here. So what we can do is in GeoGebra, and you can kind of play around with these features. They're relatively intuitive when you see the picture. I see a sphere here that looks like it has some sort of center and some sort of point. So we've got 2 options. We have a sphere with a center and a specific radius, and a sphere with a center through a point. That's what we want in this particular case. So I believe what you would want to do first is select the center. Yep, select center point and then the point. So we want the point P to be the center, and then we're going to go out to point Q. So notice I can kind of adjust the radius. And there we go. There's the sphere. If you go back to the move tool, you can kind of play around with it a little bit and see that it has the point centered at P, and then it extends and the point Q is on the sphere. And it gives us very nicely the equation, which is, notice, x minus 1 squared plus y minus 2 squared plus z minus 3 squared equals 14. Exactly the same thing that we got here. Now why don't you go ahead and give this a try. Find an equation of a sphere with the center at Q and it contains the point R. So go ahead and pause, and I'll see you back here in a few minutes. Make sure you also do it in GeoGebra as well. Welcome back, and let's see how that went. Okay, so just as before, we know the radius is going to be the length of the distance between the points Q and R, which we found already to be the square root of 57, right? And then we have this as being the center. So we would have the equation x minus 2 squared plus y minus negative 1, which would be plus 1 squared, plus z minus 5 squared equals the square root of 57 squared, which is 57. Okay, let's go ahead and graph it in GeoGebra and see how we did. Okay, I'll go ahead and hide that, and now I'm going to get rid of the point P and show the point R. we'll again use this tool of sphere with center through point. And the center was Q, and then it went through the point R. There we go. That's a big one. And if it's kind of coming out of the screen, or if you're not able to really see it how you want to, you can just do that move. Let me do this way. I'm just going to reorient so I can see all three axes. And now I'm going to do the move graphics view just so I can zoom out a little bit in all the different directions. There we go. Now we can see it a little bit better. And it might not look like a sphere just because of the dimensions, but it is. And there we go. Very cool. Okay, just one more to go here. You've been a trooper. So let's find the center and radius of this particular sphere. So now we actually have the equation of the sphere, and we want to know where is it centered and what's its radius. And the way that we're going to find that out is by trying to rewrite it so that it's in its standard form, like so. And that's going to involve one of students' favorite things to do. I'm being sarcastic. And that is completing the square. I know. So the idea is that we want to try to write this as x minus h squared plus y minus k squared plus z minus l squared equals r squared, right? So in this case, we already have an x squared, and so I can see that the h component is 0. But I can't quite tell what the k component is or what the l component is because these squares are not completed. So the way that we can do that, I'm going to go ahead and take the original and leave myself a little bit of space, is we're going to add something here to complete this square. I'll go ahead and just do plus something. I'll just do a blank spot for right now. Plus z squared plus 2z. We need to add something else in order to complete that square, and that's going to equal 4. Now the thing is that if we were to add a number to the left side of the equation, then we must also add it to the right side of the equation to keep our equation balanced. And similarly, we would need to also add whatever we add to the z component to complete the square to the right side of the equation as well. So now the big question becomes, well, what are these things? So what number needs to go in the blank in order to complete the square? So we would end up wanting to add, so there's a few ways you can think about doing this. We know that we want this to be written as y minus something squared. And the reason why I know it's a minus is because this is a minus here. And so you can kind of think about what that would have to be in order, like for this number to create a 4, when I square it, well, it's not really squaring it, it would be 2 of them, wouldn't it? This would have to be a 2. Because then I'd have y minus, it'd be a negative 2y minus 2y to give me the negative 4y. So this would have to be a 2. And then when I square this to get the part here, this would end up being 2 squared, which is 4. Okay, and then I would also need to do something similar to this one. This would need to be written as y plus something squared. And again, I know it's a plus because I've got a plus here. So whatever goes here would need to be something y plus something y, z. Sorry, I've got y's on the brain apparently. Whatever number goes here would be something z plus something z would have to give me 2z, and it'd have to be the same number, right? So this number here is always going to be half of this number. So notice this 2 was half of the 4. This is going to end up being a 1, and then I square that number. 1 squared gives me 1. So I've added 4 to the right side, to the left side, and so correspondingly I need to add 4 and 1 to the right side to keep the equation balanced. Okay, hopefully you followed that, completing the square okay. Just as a main reminder, when you're completing the square, if you've got x squared minus, I'll just say ax, the thing that goes here to complete the square is always going to be half of a and then squared. And that's always going to result in x minus half of a squared. Okay, so just have this number, and that's what would go here, and square it, and that's the thing that you're going to add to both sides. Okay, so I know it may have been a little while since doing that. So now what we have on the left side is x squared plus y minus 2 squared plus z plus 1 squared equals 4 plus 4 plus 1, which is 9. So that shows me then that the center must be the point 0, 2, negative 1, and the radius, well, the radius squared gave me 9, so the radius must be 3 then. Let's double check our answer. Okay. Oh, it's been spinning this whole time. Must be so tired. Okay, it was x squared plus y squared minus 4y plus z squared plus 2z equals 4, I believe. Let me double check that. Yep. Okay, and so notice we have that, and now it's a little hard to tell what the center is, but what we can do, I'm actually going to kind of zoom out my x direction here just so it looks a little bit more spherical. That looks pretty good. What we can do is we can plot what we found, right? We found the center to be the point 0, what was it? 0, 2, negative 1. Double check. Yep. And then we found the radius to be 3. It's a little hard to tell, but what I could do is, if the radius is 3, I'm going to go ahead and get rid of the equation for a second and do sphere with center and radius. So it's going to have me select this point and then enter the radius. In this case, we said that we thought the radius was 3. And notice that we get this sphere, which is now after completing the square, we can compare it to this one, which is the kind of more expanded, simplified form. And notice that they are the same sphere. Cool. So there's our answer check. Well, I hope you enjoyed exploring 3 dimensions. We're going to continue to keep looking at that. We're going to be looking at vectors in 3-dimension, in 3 space, and we'll see some applications, and we'll see some really cool graphs of surfaces in 3 dimensions as well.